All right, recording. Welcome back to the 12th lecture in our arithmetic harmonic analysis course. So we're actually finally getting to combining those first two words in the course title, and by talking about the arithmetic spherical maximal function, which is probably more commonly referred to as the discrete spherical maximal function. But I'll get to why I prefer this nomenclature. So we've had a few weeks or a few lectures off at least from counting points on spheres. So I'll just remind some notation there and some of the things we've already done, as well as introduce a little bit more notation. So because I want to emphasize some of the algebraic aspects of things, I'm actually going to, instead of writing, previously I'd written sort of looking at integer points on a sphere as something like this. I'm actually going to write that that sums of squares out as some quadratic form, Q. And so the sphere of radius square root lambda, centered at the origin, has integer points on it for a certain lambda. And I'm going to call the set of integer points S of lambda. Right, so implicitly in the notation for S, I should make explicit the dimension, but I won't, I leave it out. Sort of, we'll fix the dimension and always work with dimension at least 5 for reasons that'll become clear soon. And what we saw, right, in the previous set of notes is that we get asymptotic formula for the number of integer points on a sphere of radius square root lambda when lambda is a natural number. And in particular, that this is the set of such integer points is non-empty. It has positive, it's growing actually, as lambda goes to infinity, as soon as we have 5 or more dimensions, as soon as d is greater than or equal to 5. And it's actually true that S of lambda is non-empty for every lambda that's a positive integer, whenever d is greater than or equal to 4. When d is less than or equal to 3, this isn't the case. The example we've seen before is taking lambda equal to 7, for instance, or whenever it's congruent to 7 mod 8, you don't have lattice points on it for spheres in 3 dimensions in R3. Yeah, so that's just some notation we'll be using. And we need that because we have to define a Maxwell function. To find the Maxwell function, we need to define a sequence of operators. And those operators are going to be our arithmetic spherical averages. Each of these averages is given by convolution with a particular measure, which I'll call the arithmetic spherical measure. So what is that measure? It's going to be given by the characteristic function of the set of integer points on a sphere of radius square root lambda, centered at the origin, normalized by the number of points inside that set. So that makes this a probability measure, right, for each lambda. At least whenever d is greater than or equal to 4, right, when we're in 4 or more dimensions. And a probability measure is just a measure that has mass 1. This is a measure on ZD, right? And the way we measure things is we just count points with their heights. Great. Okay, so this made sense for every lambda in n for as soon as dimensions greater than or equal to 4. And we define our averages as a convolution with these normalized measures. And then you can define the full maximal function or arithmetic spherical maximal function point-wise as just a supremum over all the possible averages at each point. Right, convolution means I look at the average of f at each point x. Let me rewrite that. So at each point x, I look at the sphere centered at x of radius root lambda, and I sample all the values of my function at those points. Then I normalize by the number of such points, and that's my average at x. And I take the supremum over all these possible averages. This is for a function that itself was already defined on the integer lattice on ZD. Okay. And when I say it's defined on ZD, I just mean at every point in ZD, it has a finite value, right? And it could be 0, for instance, but it'll never be infinity. So it's different from LP functions on RD, which weren't even defined on a set to measure 0. They could have been anything. But here, there are no sets of measure 0 inside of ZD. Every point has mass at least 1. Every point has mass 1, and therefore every subset, non-empty subset, has mass at least 1. And the mass of each such subset is just the cardinality of that set. Okay, great. Along the way to proving what we want to know about the full maximal function, we're actually going to need dyadic maximal functions. So I'll introduce those now. Basically, so I have these little lambdas that are in n, and I'm going to have a big lambda now, which is also in n, and it's going to be parameterizing a dyadic range of little lambdas, okay, as in right here. Now, for each one of those big lambdas, which again is in n, a natural number, I define the dyadic maximal function at scale lambda, where it's just the supremum over the averages, a lambda, where lambda is between big lambda and twice big lambda. Okay, but again, all the little lambda are going to be natural numbers. I don't ever choose anything that's not a natural number, because there are no points on the there are no points on a sphere of that radius, and sorry, no integer points on a sphere of that radius, and therefore it doesn't make any sense to take an average. Or if you did, you'd be averaging over nothing, which would just be 0. Great. So the first property we have, these static maximal functions are bounded by the full maximal function, because the supremum for the full maximal function is just given by looking at all lambda over the natural numbers. And the supremum for the dyadic maximal function is looking at just some subset of those, right? So I have a collection of numbers at each point. I choose the biggest one, but if I look at a sub collection of those numbers and I choose the biggest one there, that's at most the maximum over all the possible, over the whole collection. So that's how we get this pointwise bound. But we also have another, we have an identity, and that is if I took the supremum over all the scales simultaneously, all these big lambdas of each of the dyadic maximal functions pointwise, then I would recover the full maximal function. What this tells us is that if we look at LP norms, and I should have written this as little LP of ZD, we can bound the LP norms of the dyadic maximal functions by the LP norm of the maximal function. And if you look at the supremum over all the possible dyadic ones, LP norms of dyadic maximal functions, it's still bounded by the maximal function, the LP1 norm of the maximal function. So just to be precise, I'll write out what the LP norm is, right? If I have F, which goes from ZD to C, then the little LP norm of F is just the sum over all the points in ZD of F at those points to the pth power. And then you take the 1 over pth power. That's the LP, little LP norm on ZD. And of course, the little LP space is all the functions on ZD, complex value functions on ZD, which have a finite LP norm. Cool. So what's the theorem, or what's the first theorem that appeared regarding these maximal functions? Well, Magyar introduced the dyadic maximal functions, and he proved that each of them is bounded on little LP of ZD as soon as P is big enough and the dimension is big enough. So what is big enough here? The dimension has to be at least 5 or more dimensions. Okay. And the P in the LP norm, the integrability exponent, has to be at least the dimension over the dimension minus 2. Now, when d is greater than or equal to 5, this exponent here, d over d minus 2, is always less than 2. And when d equals 4, it is 2. But he doesn't prove anything of that flavor for d equals 4 because it's not true. Well, the corresponding result is not true. His theorem is true. I haven't made it too explicit in the statement of the theorem, but I want to point out right now. The point is that each of these maximal functions, right? So I'm saying this is a bounded operator, my m lambda of f, which is this thing right here. This is at most some constant times the LP norm of f. So p bigger than d over d minus 2 and d greater than or equal to 5. This constant c right here does not depend on lambda. It's uniform in all of the lambda. So any of the dyadic maximal functions are uniformly bounded. Okay. Now we saw when p is greater than or equal to 2, and we were working over RD but not ZD, so over Euclidean space. We saw that we could use, if we had a maximal operator that was frequency localized, meaning the underlying average was frequency localized. When p is greater than or equal to 2, we could use a dyadic maximal function and a bound there to get a bound for the full maximal function. And we only lost a constant of like 3 in doing so. We could go to m of lambda. Sorry, not m of lambda, just m, the full maximal function, with a constant of at most 3c when we add this. But that's not the case here. We don't have any sort of statement like that. And it's because ZD has no dilation. It doesn't have the same dilational structure that RD has. Okay. There is some dilation structure in there. For instance, I can send ZD and I can dilate it by some natural number Q, say, to send it to QZ to the D. Those are isomorphic sets, but I can't shrink it by, say, a half. That's no longer integer points, right? I mean, I have a bunch of points that are integers in there, but I have a bunch of points now that are not integers. And that's a difficulty. So there's no such, the point being, there's no such theorem like that one that said that we can leverage some information about a dyadic maximal function in Euclidean space to the corresponding full maximal function in Euclidean space. We have to do something different in this area. Another way of saying that is there does not seem to be an appropriate analog of Littlewood-Paley theory over the integers. Okay, so I want to give a nice short proof of Magyar's theorem. Well, actually, just a very special subcase of Magyar's theorem. When D is at least 8, and we consider L2, should be an L2. We'll prove boundedness on L2 for this when D is greater than or equal to 8. And the proof for this essentially goes back to work of myself with Tess Anderson, Brian Cook, and Angel Kumchev. But we didn't record it anywhere, so I'll do that in this case. It's very simple and straightforward. And it shows how arithmetic comes into play in these things. But before getting to anything like that, let's state what the main goal is. Our main goal is actually to prove Magyar Stein-Weinger's theorem, which says that the full maximal function, full arithmetic spherical maximal function, is bounded on LP for that same range of P that was in Magyar's theorem and the same range of dimension. Right, so D is greater than or equal to 5 and P is greater than D over D minus 2. So this range is actually sharp in P and D. And I will actually show you why it fails whenever D is less than or equal to, less than or equal to 4 right now, or less than or equal to d over d minus 2. Let's switch to black color. Don't know how to do that. All right, cancel. Okay. So what are the counterexamples in this case to the putative theorem? Well, it's actually very simple. What we're going to do is we're going to take f to be about the simplest function you could possibly imagine. It's just 1 at the origin and 0 otherwise. That's just the delta function at the origin, right? Technically, the simplest function you could probably imagine is the function that's 0 everywhere, but that doesn't give anything interesting. All the averages are 0, the Maxwell function is 0. This actually starts to pick up some behavior. Okay, so we have m f of x at each point x and zd is actually just the supremum over all lambda that are natural numbers of our averages, right? Well, this is going to be greater than or equal to any choice of lambda that I put in there that can depend on the point x. So I'm actually just going to do this. I'm going to say this is greater than or equal to a of lambda equals x squared, which remember is q of x at the point x. So what is this? That's just the 1 over s of q of x times the sum of all x, well, not x, sorry, m in q of x, f of x minus m. But this is actually just a delta function, right, at the origin. So this is only 1 when x is equal to m, and 0 otherwise. But I chose the sphere whose radius is the square root of x, so that I have a point on here, namely x itself, right? So this is equal to just this whole sum is actually just equal to 1. And so we actually just have that this is greater than or equal to 1 over, oh, sorry, this is the cardinality. The cardinality of the number of points on the sphere of radius square root of q of x. And well, okay, we studied what that was in the first few lectures, right? We know that the number of such points grows like, well, some constant, it's asymptotic to some constant that was measuring the d minus 1 dimensional volume of the Euclidean unit sphere, and then times some singular series, which is this crazy math frac symbol that's supposed to be an s, and times lambda to the d over 2 minus 1 as lambda goes to infinity. Plus some, there's some error term here that is a smaller exponent than d over 2 minus 1 in terms of lambda. But we could say that this is greater than or equal to some constant times that, right? And in particular, less than or equal to some constant times that. And in particular, this constant, and coming from the singular series, yeah, it fluctuated depending on lambda, but we always saw that it was between some, it was always away from 0 and away from infinity, right? In a way that's uniform in lambda and only dependent on the dimension. So we can say there's just some big constant here that we don't have to write down. This is at most just lambda to the d over 2 minus 1. We actually get upper and lower bounds of this flavor. Great. So this tells us that these are, that mf of x is at most what? The absolute value of x to the 1 minus d over 2. Great. Let me record that. If delta, the delta function has Maxwell function greater than or equal to, well, up to some constant, x to the 1 minus d over 2. For every point x in zt, not equal to the origin. Okay. At the origin, it is 0. Now, because I didn't define an average of over just a single point. It had to be over a actual sphere. Now, all we do is we just look at this m delta naught of x. When is this an LP norm? At most some other constant, c prime, the LP norm of f. Right? Or where f is delta here, sorry. Well, this is just 1 right here. So this is actually just saying, when is this LP norm of my maximal function, of this function right here, bounded, when is it finite? And we're going to see that, well, the computation is going to show that this is not enough decay whenever p is less than or equal to d over d minus 2. So let's actually just take p equal to d over d minus 2 and see why. So we have that the sum okay. The p norm is finite if and only if this p power sum is finite, right? By just taking p powers. So this is at most, what is it? X to the 1 minus d over 2 to the p, but p was d over d minus 2. So this is equal to x to the what? 2 minus d over 2 times d over d minus 2, which is equal to x to the minus d over 2, which means I made a mistake. Yes, the mistake was, this was lambda to the 1 minus d over 2, but lambda is square root of lambda is the absolute value of x. So what I should have written here is actually x to the 2 minus d. And that means that this is there, and we just have x to the minus d. And we know that that's not a summable sequence. That's infinity, right? Sorry, oh, I should have summed this. Greater or equal to the sum, greater or equal to the sum, and the sum. And that is infinity. And for smaller p, it only gets worse, right? This is going to be an exponent here, that minus d, that is even smaller, so has less decay and it still diverges. Great, so that's why the Magyar Stein-Wainger theorem is sharp in the range of p. Let's discuss in the range of d. Oh, didn't get there. This was assuming all d was greater than or equal to 5, remember. Right here. For d greater than or equal to 5 by our first lectures. Now, if let's say if d is equal to 4, okay, then, and we haven't proved this fact, but it's a very classical fact from number theory. I think Lagrange or Legendre, I forget which one. But it just says that the number of integer points in Z, so points in Z4, such that x is equal to x squared equals 4 to the j is 24 for any natural number j. All right, so let me rephrase it this way. The number of ways to write a power of 4, an integral power of 4, positive integral power of 4, as a sum of 4 squares is exactly 24. There are exactly 24 ways to write any power of 4 that way. Okay, so what does that mean for us? Well, that means when I plug in that bound up here, I don't get any decay on this function. The Maxwell function is always bounded below by 1 over 24. That's because it's 1 over the number of points in the average, right? And since there's no decay, there's no way I can have a finite LP norm, right? I'll add the sort of the J is an infinite sequence as J goes to infinity. And on each one of those spheres, there's 1 over 24. There's 24 points, each of height 1 over 24. And so I sum up what's going to be an infinite a divergent sequence. Okay, and the same problems hold in 2 or 3. There are a lot of spheres that don't have enough points on them. Okay, so that's the sharpness and the dimension as well. I didn't say this, but I'll make it clear now. That's the p less than infinity, right? If d is less than or equal to 4, you do get, that's weird. You do get boundedness on L infinity. And that's just because if you start with a bounded function and you convolve with a probability measure, you spit out this bounded function as well. We saw that happening in the Euclidean setting as well. The real interest here is in the finite p. Okay. Are there any questions at this stage about the sharpness? All right, going forward then. There's also an endpoint estimate to this. So we saw for Stein's theorem that the continuous Euclidean spherical Maxwell function was bounded on LP of RD whenever D was at least 3 dimensions, and the P was greater than D over D minus 1. So Magyar, Stein, and Wainger's theorem says a very similar thing, but now everything's discrete, and we have to have D at least 5 with P greater than D over D minus 2. Now, so a refinement of Stein's theorem was Bergain's restricted weak type theorem, which said that at that endpoint, D over D minus 1, the continuous Euclidean spherical Maxwell function was restricted weak type. And Ionescu proved the corresponding theorem for the discrete, or the arithmetic spherical Maxwell function, right? He showed that at the endpoint, D over D minus 2, we have this restricted weak type theorem, which is just the same as this statement. You're bounded from this Lorentz space to this other Lorentz space. So another way to say this is restricted weak type D over D minus 2 to D over D minus 2. And that has the same interpretation as before. What we end up looking at is we look at the super level sets of M. So if I take my function f, I want to look at when MF is greater than alpha, and I want to know the measure of that, okay, which for us is actually just the cardinality. And I want to compare it to some power of alpha, which for this case is D over D minus 2, times the LP norm of f. So this case it's D over D minus 2, and this is to the D over D minus 2. But where f is the characteristic function of any finite set inside of ZD. Great. All right, I'll pause a minute to take a sip. When you do that, you end up getting f to some power over here. The cardinality of f to some power. And this is a refinement because when you interpolate with that trivial L infinity bound, you recover the Magyar-Stein-Wainger theorem. Okay. So we won't prove Ionescu's theorem, I believe, or we'll use the style of proof to prove Magyar-Stein-Wainger's theorem. The reason why we don't quite get his theorem is that when I do the circle method, I will not be using theta functions to decompose to divine the averages and decompose them. Instead, I'll use a simpler smoothing, and that will carry an epsilon loss like we had when we studied a number of integer points on spheres. And that epsilon loss just barely forbids me from getting this endpoint, but I can get the same bound for any p greater than d over d minus 2, and interpolation boosts that to a strong type inequality for any bigger p, and as long as I can take p closer and closer to d over d minus 2, I can get any other p. Great. So are there any questions before I give a proof of the L2 boundedness of the dyadic maximal function? Bear in mind, I can't actually see if anyone has any questions, so just speak up. Okay, carrying on. Here's the actual theorem I want to prove. And again, this is just a weak version of Magyar's theorem. So I'm considering these, oops, that should be a big lambda. Let's make that, not that one. So you give me any big lambda, that's a natural number. I'm looking at these maximal functions, dyadic maximal functions. And now when I have at least 8 dimensions, this dyadic maximal function is bounded on L2, and that norm doesn't depend on lambda. Now, when d is equal to 6, the norm is going to depend on lambda, but it's only going to be log lambda. Right, so remember, this is called m sub lambda of f. So in particular, I'm saying there exists a constant depending on d, such that m lambda of f on L2 is less than or equal to c of d f in L2. And here, I'm saying there exists a constant c depending on 6, such that similar statement holds. M lambda of f in L2 is at most a constant times log lambda times the L2 norm of f. Now, the reason I'm being precise about this is because actually each dyadic maximal function is a bounded operator on L2 by just the union bound. So what do I mean by that? It's actually a bounded operator on any LP space. So why? Let's just take the union bound, which says I take the sup over lambda to 2 lambda of these averages. And that's at most, okay, at each point x, that's at most the sum over lambda in that range. Therefore, if I look at the LP norm, I get this bound. But you can actually do even better by the triangle inequality applied to LP norms. I can move that inside and get those bounds. So now you don't have to worry about that. And now I just observed that since a lambda is given as convolution with a probability measure, that's a contraction on any LP space. We saw this several lectures ago. And so this is always less than or equal to sum over lambda and lambda, range of lambda to 2 lambda, of the LP norm of F. And that's, of course, just lambda times the LP norm of F. So each of these dyadic maximal functions is a bounded operator on LP. This worked for all p greater than 1, or greater than or equal to 1. But the annoying thing here is that these norms they depend very much on lambda. And you can't apply them when you want to study the full maximal function, because this means when I take the supremum over lambda, that are natural numbers, then this bound right here goes to infinity. And I don't get to say anything about the full maximal function, let alone this weaker variant where I've souped on the outside. Okay, but Magyar's theorem says that you can actually put an explicit constant here, and I'm saying that that's true. I'm saying we'll give a nice proof of that when d is at least 8, and you can put a log there, which is already beating lambda by a whole bunch, whenever you have d equals 6. So let's see why that's true. It's going to come down to one analytic input and one arithmetic input. So let's see what the analytic input is here first. Okay, fix our lambda to fix our dyadic spherical maximal function. And now consider Fourier multipliers of the following shape. So I'll let t of lambda be my convolution operator acting on L2, defined by the Fourier multiplier of this m lambda hat. I don't think I wanted a hat there, actually. Well, yeah, maybe. And okay, so what's this? Well, this of course is e to the minus 2 pi I theta minus lambda theta. And this function here, k, is actually just going to be an L1 function in terms of the first variable for each point c. But it's also going to be a function that is independent of lambda. So what I'm saying is that in this convolution t of lambda, all the dependence on lambda lies in this phase right here. Right, and then yeah, so I didn't want that. So remember, t of lambda is, since it's a convolution operator, and I'm saying this is the Fourier multiplier, it means that if I look at the Fourier transform of f, then this is by definition m lambda times f hat. And so then taking the inverse Fourier transform of this turns this into convolution. That's the inverse Fourier transform convolved with f. And this is for a function f defined on ZD, because this multiplier right here is assumed to be defined on the torus. That's where these are coming in. Great, okay. Now, I still need to define the Maxwell function, and I'm defining just a dyadic one. And you can say that the dyadic Maxwell function is bounded on L2, and its norm is bounded by this integral, this mean value of a sup norm. Right, so I take an L1 bound of an L infinity bound in differing variables. Great. So I haven't said how this relates to the average at all yet. But let's go ahead and sort of see where this is coming in, or let's give something simpler first before we see how to prove this. So there's a very straightforward bound if I were just to have a single L2, sorry, a single average instead of this dyadic maximum, right? So assume that t of lambda is defined just as above. Again, it's convolution with the inverse Fourier transform of this multiplier. And now you want to know its L2 norm. It turns out its L2 norm satisfies this bound, where I do the L1 norm of my function first, and then the L infinity norm. To compare this with the thing above, these have switched order, right? This is over here, and that's over there. Also, remember, when the supremum is on the inside, it's going to be a bigger operator, or a bigger function in this case, and therefore it's going to be harder to bound from above, right? In other words, this bounding a single t of lambda on L2 should be easier than bounding the dyadic maximal function, and the bounds we get and how we do these two things are reflecting that. Okay, this bound right here is going to be easier to bound than this bound right here. Okay. The way you do this is pretty easy. So let's just go through it real quick. Are pretty straightforward. T lambda of f of x. I want to bound this in L2, right? So I fix my function f in L2. And well, I apply Plancherel's theorem. That's the beauty of L2, right? I'm going to use Fourier analysis. So this is going to be this Fourier transform on L2 of the torus. This is ZD. And well, that's just a multiplier. That was m of lambda times f hat on L2 of TD. Now you just apply the usual L infinity bound. That's at most the sup of m lambda and L infinity of the torus times f in L2 f hat. But you apply Plancherel again to remove the hats and to make that little L2, so that our problem just reduces to bounding this. And so my claim is going to be that this is at most this. All right, but what was m lambda? It was defined as the integral from x k theta c e to the minus lambda theta d theta. And right, and this is an infinity in terms of c. And so, yeah, you just want to know the supremum in c of this thing, then that's just the sup over c of that, which is all I've claimed. Well, actually, I've claimed something slightly stronger. I just moved by the triangle inequality. I just moved this absolute value inside. So it's pretty straightforward. There's nothing really sophisticated being done there. The point is that this inequality is a stronger and more useful inequality. Great, so let's go into how to prove that. Now let me pull up my notes. All right, so let's start with what we were just saying. Write out what t of lambda fx is. For the blue. T lambda f of x is once again just the absolute value of, well, it's the inverse Fourier transform of a Fourier transform. And when you write that out, that's just this, the inverse Fourier transform on the torus of this function, which is an integral itself. You have x dot c minus x dot c times a Fourier transform of f. And that's with respect to theta and c. Let me just take a quick digression because I didn't do this before, and I should have. So when my function f is on ZD, goes to the complex numbers, say it's compactly supported, so just taking a finite number of values, but really we just need it lying in L1. Then the Fourier transform, so it's Fourier transform on ZD to the torus, is just defined as the sum. So I'm going to call that f hat at a point C, which is in the torus, the d-dimensional torus. Oops, that's defined. As a sum over all the lattice points, all the integer points, ZD, f of m e m dot c. It's inverse Fourier transform. So if I start with the function f, say, on the torus, that's complex, and it just needs to be integral on the torus, which means the big integral, or with respect to hard measure. So it's TD to ZD Fourier transform, which is the inverse Fourier transform of the ZD to TD transform. Fourier transform is defined as the integral. So I'm going to put a check here because I can write checks, but often I'll just write a hat and abuse notation here. It's the integral over TD f. I'm sorry, that's a big F. F of x e of minus x dot. Ooh, that shouldn't be xc. Let's say m. Okay, that's the inverse Fourier transform to take you back to the torus. Great. Right, so that's so in particular, I'm using that right here to define f hat, and this multiplier was m of lambda of c. Brilliant. Now, that digression aside, let me just say this is less than or equal to, well, just apply Fubini's theorem and move the absolute value inside. So it's the integral over x of the integral of the absolute value of the integral over the torus of k of theta xc f hat of c e to the x dot c plus minus theta lambda. And that's with respect to dxc and d theta. Oh, sorry, I want the c in there. Right? Now, the dependence on theta on theta in lambda is right here. But that integral doesn't depend on it at all. On that right there. So I can pull it out of the integral, and it's just modulating the integral, which means that I can just cross it out. Actually, when I take the absolute value, that's a 1. I don't have to worry about that at all. Okay, so let's make that look a little bit nicer. Basically, what I'm saying is that we have this inequality. All right. And now you see, this doesn't depend on lambda at all. So in particular, we have t over lambda f of x is less than or equal to this. And since the lambda doesn't depend on there at all, it's actually the same thing for the Maxwell function at each point. Okay, so I'm going to call this inner expression g of, I want to say theta x. Right, coming from this x right there, and that theta. Great. Okay, so we have the fact that we have this right now. If I take t star f in L2, that's at most the L2 norm of the integral of x of g theta x d theta. Where the L2 norm is just over the little x. These are ZD. So that's little x and ZD. I'll just apply, oh, sorry, that's less than or equal to. So just apply Minkowski's inequality now. And, oh, sorry, it's the less than or equal to. Apply Minkowski's inequality because that's an L1 norm on the inside. And an L2 norm on the outside, which means when you switch them, you can switch them by Minkowski's inequality. So you get an L1 norm on the outside of an L2 norm inside. And now, again, Fourier analysis. So what are we going to do? We're going to apply Plancherel's theorem. And so we rewrite that as the Fourier integral. So this is now equal to the integral over x of, I want to say, actually this, I'll just write it like this, Fourier transform L2 of TD by Plancherel. And so what is this? This is just going to be, well, this happens to be, let's write it to the side here. G theta of C is of course just K theta C Fourier transform of F. And so the absolute value of it is just that. And the absolute value squared is of course that. So that this right here is at most K theta C is a Fourier transform squared. And I integrate with respect to C and then theta. Okay, Bessel's inequality. Now we take the soup. Oh, sorry, I didn't write the integral over C. It's over the torus. And now I apply Bessel's inequality, so that I take the soup over C and the torus of K theta C squared. Oh, sorry, this is to the, these are all to the 2th power. There we go. All right, times the f hat of C squared dc and d theta. But this is now something I don't have to worry about. I can pull out. Oh, I didn't write the integral over t. Sorry, the integral over td. This part is, of course, just the L2 norm of f on td squared, which by Plancherel's theorem, again, is just f and L2, little L2 squared. And we get to pull that out because it's not depending on theta or, it's not depending on theta. So it's equal to the L2 norm of f squared times the integral over x of the supremum of this thing. And I think I made a small mistake. I probably should not have done the L2 norms, and I should have written this. Yeah, I should not have. In catching my mistake, I was a bit hasty in terms of correcting it. Sorry. Deletes. So the L2 norm is there, and I should put this here. And then I don't have that square there. And I should have had a, let's just erase this. I should have had a 1/2 there. Okay, and that's how you prove it. That's the corrected way. I still gave myself another slide. I suppose I could have made that clearer there. But in any case, that is the main inequality, which I'll just bring up to remind you. Right, I have this sort of multiplier, which is defined for the moment in a seemingly overly wrought way as some function times this modulating factor. And then I say you can bound the L2 norm of the dyadic Maxwell function by taking the supremum over the worst of these C that arise. And that's how we're going to get rid of this modulating factor that comes into the definition of our multiplier. So how do we use it? Well, we're going to write down the Fourier transform of our multiplier, which I haven't done. So I had this, I had sigma of lambda was defined as 1 over the number, there's this probability measure, right? Where I normalize by the number of points, integer points on a sphere of radius square root lambda centered at the origin, times the indicator function of that set. I can take the Fourier transform, and this at a point C, well, by definition, it's 1 over the number of integer points on the sphere of radius square root lambda times the sum of, well, E x dot C, where x is in S of lambda. And what we're going to do is we're going to use that same delta method we used at the very beginning. I'm going to write a point being inside the sphere as if it satisfies the following. So recall our orthogonality relation. Our primary one was E of, let's say, Tn dt from 0 to 1. This is equal to 1 if n was 0 and 0 otherwise. Well, we can make that useful for us by saying if this is q of x minus lambda, this is then if x lies in S lambda. So plugging that into the above, I just have the fact I have that one of S lambda hat of C is going to equal a sum over all lattice points, and then the integral from 0 to 1, e of t q of m minus lambda plus m dot c, and all with respect to dt. This doesn't quite, this doesn't seem to make very rigorous sense because, excuse me, because, right, I don't know a priori that this has only a finite set, but you just simply squeeze in our smoothing factor. So we're going to say this is m over r, whenever r is at least the square root of lambda. And this is basically the exact same Fourier transform we had before. This time, though, we're going to have to pay a lot more attention to what happens with these linear twists, right? So I can rewrite this by applying Fubini's theorem as the integral from 0 to 1 of the sum over all integer points, phi of m over r, e of this expression. Right? And this would have looked a lot closer to what I've written before if I just pull out this factor. So instead, I'll write this as just qm, and I'll write this so that e of minus lambda t dt, like this. And so you can see that this as the expression of k of t c from the main L2 inequality. Okay. So that's how we're going to use it shortly. And let's see why. Yeah. So related to this, sorry, let me bring this back up. Before, at least in the proof for a Hartley-Lewis theorem, remember that I chose phi. I chose phi to be a tensor product. So phi of a vector was equal to a product over each of the coordinates of some one-dimensional phi of m, phi naught of m, right? And so I still want that here. That's useful for us. And what that allows me to do is it allows me to split up this kt right here, because the q of m also is has a tensor product structure. It's a sum of squares, which with interacting with the e turns into a product. And the same thing happens with this dot product here. So in particular, what I have is I have that the above, this is the sum, is going to be a sum over a one-dimensional m in z, phi naught of m over r, e of t m squared plus m dot c I, and then my product from I equals 1 to d. All right. And when I take this, I'm looking for the soup. Remember, I want the soup here over C in the torus. Since this has a tensor product structure, I'll call each one of these alpha of TCI. when I look at the absolute value, sorry, you want the absolute value of this, then it's equal to the absolute value of the product of the absolute value, sorry. But these factors alpha are all the same. And that means that I can assume that all the Xi are the same. The soup, if I had two values at Xc1 and Xc2, such that alpha of Tc1, I have alpha of Tc1 and alpha of Tc2 as well, and these are two numbers, and one of them has to be bigger than the other, or at least bigger than or equal to, right? And then I know that the supremum for this product would be bumped up if I just inserted the second one, the first one in place of the second one, right? So this is just the same as, this is actually equal to the soup over C in the one-dimensional torus of alpha of T C to the dth power. Okay. And now what I want to happen, or what I'm going to do, is I'm going to reduce this supremum problem to when D is an even integer, positive integer, to a mean value estimate. And what does that mean value estimate? Oh, the end brackets didn't show up here. So assume for simplicity at the moment that phi naught is, or sorry, phi naught is just 1 from -1 to 1 and 0 otherwise. Okay, so it's a sharp cutoff instead of a smooth cutoff. We'll go back to the smooth cutoff shortly. But what we have is that this supremum, which we'll call when this is D, that's what we're looking for, we get this bound. It's going to be, so if I have my sum, it's from -n to n now instead of r's, then it's at most n times the number of points satisfying these equations. Oh, there should be two s's. I'm sorry. That should be an s. Nope, those should all be s's. S, 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 S. Okay. Up to some constant that only depends on the s. Right. This is pretty nice, actually, if I'm being honest. Okay, so how do we want to do this? Yeah, this is not at all obvious, but this is how we'll do it. Okay, I'm going to introduce a h of theta to be the sum over all n from -n to n of s, such that, this is the vector, such that the sum of the coordinates is equal to h. Okay. Of what? Of these waves. This n, oh sorry, I should say q of n. Great. So we're gonna have to watch out for this condition as we go along. But what we do is it allows us to write this product now as it's a square of these things. And yeah, so let's take s factors out. So we have alpha to the theta c is equal to, oh sorry, to the s is going to be equal to sum over h, AH of theta times EHC. And let's just drop the absolute values for the moment. Oh, cut off too much. All right, what's the range of h here? The range of h actually is I can go at most Well, how big and small can this sum be? Each ni can be at most, at most n, and there's s of them. And it can be at worst or at smallest minus n, and there's s of those too. So this is h equals minus sn up to sn. Basically, there are O of n possible choices for h. Okay. Now let's apply the Cauchy-Schwarz inequality. So I have Cauchy-Schwarz inequality. When I look at the soup overall C, one-dimensional, right, of alpha, it's an alpha, beta, C to the 2s, that's going to be less than or equal to, because I'm plugging that in here by the Cauchy-Schwarz inequality, less than or equal to the sum from h equals minus sn to sn of ones. Well, actually, I'll put it here. I'll put this here. Of the absolute value of E of HC squared. It's just a square. And times this a similar expression, the analogous one. So minus Sn to Sn of AH theta. So this is squared. And again, great. This, of course, these are all just ones. And this term right here is just O of n. And we're left with this expression. Great, so it remains to analyze this latter square sum. When we integrate, so let's now at this point integrate, right? So I actually wanted to bound the integral over the torus in terms of theta, sup of alpha theta c, 2s, and this is all c in one-dimensional torus, and average over theta. So now we have this is less than or equal to, up to some constants, n times the integral, the integral of the sum, but I can Fubinize things, so I can switch the integral and the sum. Sum over h equals minus Sn to Sn, and the integral over t for theta. Oops. And I'm actually going to write this out in a better way. So this is AH theta conjugated. This is integral with respect to theta. Great. Now let's apply Planck-Charles theorem. Okay, to find that the integral. So this integral is actually just equal to. Well, what is it from above? How was it defined? It was this definition. So this is actually just so it's the number of m and n, n minus n to n to the s, such that q of m is equal to q of n, and the sum of the mi equals the sum of the ni equals h. All right, why is that? Right, it's because of, well, the sum is restricted to those ni's having this linear condition. But when I integrate over theta, I'm going to pick out by orthogonality this condition for q because of these exponentials. Okay, so that gives me this when I actually do the integration. All right, So altogether, we have that this is at most up to some constant depending on n. It's actually like 2s or something, or 2s plus 1. Oh, right, n times this sum. But you get to absorb this sum into this set, or the cardinality here. You just drop that condition on H, right? This is equal to n times the cardinality of m and minus n to the s, such that q of m equals q of n, excuse me, and the sum of the mi's, m equals 1 to s, is the sum of the ni's from I equals 1 to s. And voila. So that's how you get our desired mean value, which is right here, sorry. Oh, I see there's something in the chat. Is the T star bound from Schur's lemma? Oops, T lambda. Yes, it's basically Schur's lemma, basically. Yeah. But I think you asked that a while ago. We can come back to that at the end if there's another question. Right, yes, sorry. So we have our bound for this inequality, for this quantity right here. And it's bounded as a mean value. And why do I call that a mean value? When it's actually counting solutions to a Diophantine equation, or a pair of Diophantine equations inside some box. That's because you can use orthogonality, just like we did right here, to rewrite this as an integral. And that integral would be n times the double integral, t of the sum en squared theta plus nc. So this is n equals minus n to n to s d c d theta, or whichever order you want there. And that's why I call it a mean value, is because it's taking the mean over this exponential sum to a certain power. Oh, hello. That was a big jump. Nope, still too big. Okay, great. Are there any questions on that? Oh, I get myself a lot of space there. All right, I don't see any questions. So I'll just prove this theorem of Magyar that I wanted to prove. We combine these two things together. And so we had that. So what do we have at the moment? We have that, if I look at the Fourier transform of this buddy at a point C, it was equal to the integral over the torus of a sum and with E of Q of M T plus M dot C. And that was times E of minus lambda T dt. All right, and we know that, so this means sigma lambda is, the Fourier transform thereof actually, is equal to this thing times 1 over the number of points S of lambda times that thing, right? Okay, but in particular, if I look at the absolute value, putting them in here, I can actually use the asymptotics we know for this to say that this would be less than or equal to up to some constant that I'm not going to keep track of, but doesn't depend on lambda, of lambda to the 1 minus d over 2 times the integral of this thing. Okay. Now the point is that when I define my averages, a sub lambda f of x, I can say that they're all bounded by lambda is the 1 minus d over 2 times f convolved with this this characteristic function at the point x, right? This isn't the actual number of points on S lambda, but up to a factor, it's always the right bound. Okay. And now what I want to do is I just take, I take these as what I plug into for my operators t. So these are going to be my t of lambda. And what do I do with that t of lambda? Well, I knew that the sup over lambda from big lambda to 2 big lambda, twice big lambda, of t lambda f of x, that in the L2 norm was at most this, how do we write it? We wrote as the integral over t times the sup over c in td of this sum, which I'll now just, I'll use that notation from above. It's a product of alpha t ci I equals 1 to d with integrating with respect to t. And then of course I have everything times the L2 norm of f. But I had that this thing was at most some mean value, right? This is at most n times my mean value, the number of m and n inside of what box? Well, I was using, I wrote it as n before, but what I'm using is r here. Oh, sorry, so I should write this as r. Then this is at most minus r to r to the d over 2. In order to make this reduction now, I have to assume that d is some even integer. Let's call it 2s. So this thing right here is just s. And such that the sum of the mi squared is equal to the sum of the ni squared. And the sum of mi equals the sum of ni. Okay, it's the cardinality of this set. But this is a classical fact. And I'm just going to quote it, but sort of indicate how one might go about proving it. So this set right here, the cardinality of the set right here, sorry, m n and minus r to the s, such that sum of mi squared equals sum of ni squared, and the sum of mi equals the sum of ni. This has cardinality at most r to the s. So let's say r is an integer, equals an integer. R to the s plus r to the 2s minus 3, whenever s is a natural number that is not equal to 3. Oops, the root 0. All right, if s equals 3, then this is at most actually r cubed log r, up to some constant I'm not recording. Right, these constants are allowed to depend on s, but they do not depend on r. All right, how would you prove anything like this? Well, when s is equal to, well, if s equals 1, this is pretty trivial, right? You just have you just take m equals n. So I have a single m1 and a single n1, and they have to be equal to each other. Great, but they can be anything between minus r, and that has a size 2r plus 1. Let's do something semi-interesting now. Let's take s equals to 2. They should all be, if it wasn't clear, I equals s, or 1 to s. Now, if you take s equals 2, I have the sum of 2 squares equals another sum of 2 squares, the corresponding linear equation. And that actually has diagonal behavior. You can use the Newton-Girard identities to show that that means that, that the set M1 and M2 must actually be equal to the set N1 and N2. And therefore, that's R squared many solutions up to a factor of 2. And you finally get something interesting happening when you get s equals 3. There, you can use this s equals 2 bound and an average bound. You can use divisors. You can adapt one of the arguments I gave for counting the number of integer points on a sphere of on the number of integer points on a sphere of radius r inside Z4 or R4. You can do that sort of bound to get, you can do something like that to prove things when s is equal to 3 and higher, but you lose this, this r to the epsilon loss that we had before. You can actually get rid of that by doing something where you average that out, so just get a log, which comes up here. And then as soon as s is greater than or equal to 4, you can actually use the circle method to get this bound, which doesn't have the log loss. And I actually have no idea how to do this without having to use the circle method. And so if anyone knows of a elementary way, or sort of a way that doesn't use basically the case s equals 3 and Weil's inequality to get rid of the epsilon loss, I'd be very keen to see that. I couldn't think of how to do that this morning. But again, if you use the circle method, you can get this bound because the major arcs will have exactly that size, and then you can use the minor arcs. You use Weil's inequality on the minor arcs to get rid of this log loss in when s equals 3 by the same methods or very analogous methods to what we did in the first part of the course, right? The first few lectures on Hardy-Littlewood method. Of course, when you do this and you have this mean value, right? That is a mean value in, where is it? In 2 parameters, theta and c. You have to do major minor arcs in both of those parameters. I won't go into further detail on that. Let's just say these are classical facts that you can apply here, and they give you exactly what we need. As soon as s is greater than or equal to 4, right? So I get this bound, and yeah, that cancels out with the square root of lambda that I'm going to lose. So r is equal to square root of lambda, and I have, let me maybe write it this way, r equals square root of lambda. So this is a square root of lambda, and these are square roots of lambda. When I plug that in here, that's exactly offsets this power of lambda right here. Yeah, don't forget this one and these ones. They directly offset that, so that you always have that this bound right here is, so this bound is always at most lambda to the d over 2 minus 1, which exactly compensates for that. Yeah. Oh, maybe I should have said, here's a key point that may trick people up. Because I assume lambda, so the suit over lambda in lambda to 2 lambda of a lambda f. So that's, I said at most, if I took this, hold on, suit over lambda, 2 lambda, lambda to the 1 minus d over 2 times the absolute value of t lambda, right? But all of these lambdas are in some bounded range. They're all about size big lambda. And so this is up to some constant again, actually a very precise power of 2, is at most lambda to the 1 minus d over 2, where that's a big lambda now times the sup. Right. And those r's, I can choose that r to be just square root of big lambda. And following this arithmetic through, you find out that exactly compensates this factor. And you get that this in L2 is at most, it has it's O of 1. And of course, when s equals 3, I unfortunately have this pesky log factor that is not compensated for right here. And so the operator norm is just as a log loss in terms of big lambda. Yeah. Where was that? Way up here. Oh, sorry, further. Yeah. Okay, great. I've gone a lot slower than I thought I did. Let's see if there's anything else, or I should wrap it up here. I will, okay, I'll go a little further. Sorry for flicking through real quick. But are there any questions as far as this simple proof of Magyar's theorem? All right, if there aren't any questions, and I would like to make one more comment, I'd just like to point out that this mean value estimate right here. So again, so we have the number of m and n from, say, minus r to r, the s, such that the sum of squares equal each other and the linear ones equal each other. So we said that this thing times one factor of r was able to bound our dyadic maximal function when with the dyadic maximal function m of lambda with, you know, r equal to square root of, oh, I should have added 2 there. Yeah, this also is a bound for the number of points where you drop the linear condition. Or in other words, for us, when q of m is equal to q of n. Oh, and that's a cardinality. So I find this particularly interesting because, all right, well, you know, in order to, why is this interesting? Basically, if I were to choose, you know, in defining our averages, I take, you know, I look at all the points m where q of m is equal to lambda, where the sums of squares of the mi equals lambda. And you need to, just in order to define the maximal function and see when it is a viable operator, you know, by testing this delta function, you need to know bounds for q of m as lambda goes to infinity. Okay. And one way to prove bounds for that is to look at the mean values, right? Which we didn't do really, but it's another way to get out the sum to asymptotics for sums of squares. And when you do that, you come exactly to this expression. All right. And now what we found out is that when we wanted to bound the Maxwell function on L2, we could look at just this expression, the first one, which is an upper bound for that. Okay. But going further, so this only works, this only gives us a sharp bound when s was equal to 4 or more, so when d was greater than or equal to 8. And to go beyond that, we have to do something a bit stronger than this. Okay. But at this stage, we already see that knowing some arithmetic information actually gives you some information on the maximal function. So I'd like to compare that with, there are other maximal functions out there. Okay, I'll describe them a little bit and then I'll stop there for today. So what are some of the other Maxwell functions? You can take, or discrete Maxwell functions. So first, the reason why I like to call this the arithmetic spherical Maxwell function and not the discrete one is you can have other spaces that are discrete and for which you can define spheres. So for instance, graphs, right? You can define a sphere in a graph as, so take a graph where it's just done by, the length is just one from one node to the next node. And then if you go 2 vertices away, there's at 2 edges to get to your point, that's like 2 and so on, right? And then the sphere would be everything that is, a sphere radius r would be everything that is r edges away from your starting point. And there's tons of different kinds of graphs. You could just think of ZD as being one type graph. But there are maximal functions studied on these graphs, on a variety of classes of graphs. And the techniques in studying those are very different. Quite often what you have is a graph that is like a tree, so it's growing exponentially. And therefore spheres have about the same size as balls, and you can do a lot of comparison arguments there. You don't use any arithmetic, right? You just use some geometry in that case. You could also do something on the hypercube. So if I take f2 to the n, and I use the Hamming weight, so n is going to be very large, and I use the Hamming weight to define spheres. But again, this is also just like very similar to what I was saying for edges. Then the spherical Maxwell function there is also well defined and it doesn't use any arithmetic to define it. And it also has a different range of boundedness than this one here. I think it's all p greater than 1, as proved by, I want to say Krauss, actually Ben Krauss, I think did this on L2. Sorry, these are finite spaces, so there's always a bound. The question is you want uniformity as n goes to infinity. And so for all p greater than 1, that was done by Ben Krauss, if I remember correctly. But for L2, that was done by Harrow, Kola, and Schul. So I forget exactly, I'm sorry. And again, that's a very different flavor from this. Okay, so that's one variety of maximal functions. The ones that are more arithmetic tend to be of the following shape. So Bergain's averages along the squares, which I think I mentioned in the introductory lecture, but if not, I'll recall them. You take f of x minus n squared from n equals 1 to big N, and your function f is on z. So studying this and its maximal function, which is a supremum over all the big N, was done by Bergain in the 80s, and that's what kicked off this whole field. But to be fair, independently, Arkhipov and Oskolkov, whose names I'm sure I did not pronounce it all correctly, they study the Hilbert transform for similar things. But it appeared in Russian. It appeared in Russian, and so it wasn't very accessible to the West, and people didn't know that they had done it for several years. So this averages along the squares is one way to do things. Is one arithmetic maximal function. You could also do instead an average over parabola, where you do x1 minus n and x2 minus n squared. So all of these sorts of maximal functions are done where I'm actually averaging along something, right? So I was averaging before along the squares, and meaning that, so I have an f of x defined as this, that, the set of squares from 1 up to big N is contained in the set of squares from 1 up to big N plus 1 squared. There's this overlapping property they have, which is very different from spheres. If you move from one sphere to the next sphere, they're completely disjoint. When you have this overlapping property, which I call averaging along a sequence, in this case, along the parabola or along the squares, your maximal function just reduces to setting a lacunary version. So sup over n in all n for a and f of x is actually at most 2 times the sup come on, times the sup over all dyadic n. So that's let's say big N and N, but now A of 2 to the N F of X, which is not something that's all true in whenever you're averaging for spheres, because then you're averaging transverse to a surface that you're dilating. This one you're averaging along longer and longer parts of the parabola. And this has LP boundedness that is all P greater than 1. And that's better than the range Magyar, Stein, Wainger get. And that's because of this averaging behavior right here, because it's going along rather than transverse. And that actually makes the problem simpler in many ways. And the point I want to emphasize, what I close with, is that the geometry of the family of sets that you're defining your averaging operators, so the way those interrelate, like the harder they interrelate, the harder the problem is, and the more subtle it can be. Like the range of LP boundedness is probably weaker than one with a simpler geometry and a simpler relation in terms of how they connect. Generally, when you average along something, that's the best sort of behavior you can expect. And so much more is known about it because there are so many more tools available to you. So sort of as a pithy way of saying this, the way I think about it is generally the harder the underlying arithmetic, such as counting points on something, is going to be the harder the averaging problem, or the harder the discrete analysis problem. Okay, so that's a bit of philosophy there at the end. Were there any questions before I end? Going once, twice. Okay, thank you very much.